In this video, we're going to go over the first derivative test. And this is a pretty easy method to find where functions are increasing or decreasing. But before we can find where a function is increasing or decreasing, we first have to define what increasing or decreasing means for a function. We're going to do that by making some observations. We're going to consider this random graph that I've drawn, and I've divided it into 3 intervals. And so just by simple observation, we can see that here the function is increasing, here it's decreasing, and here it's increasing again. Let's see what happens when we look at its derivative, or the slopes of the tangent lines to each point on the graph. In this first interval, whenever we draw the tangent lines to the graph, we see that they're always positive sloping. So that means the derivative on this interval is always positive. Now looking at the second interval, notice that slopes of all the tangent lines that we draw are negative. So the derivative is always negative on this interval. Similar to the first one, in the third interval, all of the tangent lines that we draw to the graph are positive sloping. So we know the derivative is always positive. So using these observations, we can define what it means for a function to be increasing or decreasing. For a function to be increasing on some interval I bound from a to b, the derivative in this interval always has to be positive. And for a function to be decreasing on some interval a to b, it's the exact opposite. The derivative always has to be negative. And finally, if a function is constant on an interval, then the derivative in that interval is always equal to 0. But remember from the last video that if the derivative at c equals 0 for some c, then c is a critical value of the function. Now if you look up at the graph, notice where I split the intervals. I've made one split at this maximum here and one split at this minimum, or at critical values of the graph. And the reason for that is because the derivative is continuous. What I mean by that is if you want to move from a region of positive derivatives to a region of negative derivatives and the derivative is continuous, you have to have passed through some point where the derivative equals 0, and that's our extrema. To wrap up, the function changes behavior at extrema. And this is how we find the intervals when functions are increasing or decreasing. We first find all the locations of our extrema, or critical values, to determine the endpoints of our intervals. And we check for the sign of the derivative in each of those intervals. And we only have to check one point in the interval because we know the sign of the derivative within an interval is always the same. Finally, depending on the direction of the behavior change, we can determine whether the extrema is a minimum or a maximum. And I'll show you what I mean by that. If you look up on this graph, notice that when we shifted from increasing to decreasing, that corresponded with the maximum. But when we shifted from decreasing to increasing, that corresponded with a minimum. When a function changes from increasing to decreasing, then we know that's a maximum. And when the function changes from decreasing to increasing, then we have a minimum. To show you how to properly do the first derivative test, I'll do an example for you. We're asked to find the intervals when f of x equals x cubed minus 6x squared minus 36x plus 11 is increasing or decreasing. So the first step in solving our problem is finding our critical values. Remember, we do that by differentiating our function and setting it equal to 0. And now we just solve for x. Dividing by 3 gives me this. Factoring gives me this. We see that x equals -2 and 6. Using our critical values as boundaries, we're going to cut our domain into intervals. What we're going to do is we're going to cut the number line from -infinity to +infinity at -2 and 6. I'm going to make this table, which is a sign chart, to help me in this step and the ones following. In this first row, we're going to write out all the intervals that we make. If we're cutting the number line at -2 and 6, then our first interval will stretch from -infinity to -2. And then our second interval will stretch from -2 to 6. And then our last interval will stretch from 6 to +infinity. Remember not to include your critical values because we know what the value of the derivative is at that point. It's 0. Now our third step is to test a point in each of these intervals. So since the sign of the derivative within each interval is the same, it can be any point we want in the interval. And a good rule of thumb is to pick the simplest or easiest points possible just to make your life easier. So in this interval, I'm going to pick -3, and here I'm going to pick 0, and here I'm going to pick 7. And again, it really does not matter what you pick for these so long as they're each in their own intervals. So now in this third row, we're going to check the sign of f prime of x at each of these points. We have f prime here, and we're just going to plug in each of these points to see what they are. So when we plug in -3, we see that f prime of -3 is 27, which is positive, so we're going to put a plus in our chart here. And we see that f prime of 0 equals -36, which is negative, so we're going to put a minus in our chart. And we see that f prime of 7 is also plus 27, which is positive, so we're going to put a plus in our chart. Finally, using this information, we're going to draw conclusions about the behavior in each of these intervals. This is the easiest step. Here, the derivative is positive, so we know it's increasing. Here, it's negative, so we know it's decreasing. Here, it's positive, so we know it's increasing. And as a sixth optional step, we can also verify extrema. Here, we see that at x equals -2, the graph switches from increasing to decreasing, and that corresponds to a maximum. And at x equals 6, the graph changes from decreasing to increasing, and we know that corresponds to a minimum. And that's how you do the first derivative test.